last talk today is going to be Mauricio Suárez from University of Madrid, and Mauricio.
Okay, thank you very much, Martin, for the invitation. Great to be visiting Prague. I love it here, so it's great. Roman was attacking the semantic view, and I'm going to try to revive it. So we'll see how this goes. But what he said at the beginning of his talk, and everybody else has said, also applies to mine. This is a workshop, so I'll be happy with whatever feedback I can get back. Okay, so my talk is going to be about how to understand the semantic view so that we can get through or over a number of different problems and objections that have been raised to it over the years. I was indeed going to start off by telling you about the syntactic and the semantic view, but I think now I will go very quickly through that part of the talk. And then I want to talk about two different identity claims that I think are often conflated. Clearly, they're involved in discussions of the semantic view of theories and often unhelpfully conflated. So I want to clearly distinguish them because as a matter of fact, I think one of those two claims is viable. It's the combination of the two claims that I think is problematic. And in doing that, I hope to be able to put forward a view on the semantic conception of theories that's refreshingly new and very different to the one that Roman was discussing in his talk, and which I call the representational semantic conception. And I should say, once I arrive at point 3, whatever comes in the remaining part of the talk is joint work with Francesca Pero, who is a postdoctoral researcher at the University of Florence in Italy. I'm going to start to try to motivate that new semantic conception or version of the semantic conception by talking about two different problems, the constitution problem and the application problem, as they pertain to representation. Because as you will see in this version of the semantic conception, representation takes center stage. And then what I'll do in the last part of the talk is to try to argue that this different version of the semantic conception doesn't boil down or reduce to any of the versions of the semantic conception that we have found objectionable over the last couple of decades. And in particular, it doesn't boil down to any version of structuralism. And I'll do that by showing that I can, within this version of the semantic conception, one can accommodate the use of mathematical structures in science without reducing representational theories to structures. That's what I do in the final two sections of the talk, and finally I just end up with some conclusions where I just sum up, hopefully, what I do throughout the talk. So let me very quickly go through the first part, the first point, and I go very quickly through this because this list of problems with the syntactic conception is a minor. I thought this was a long list of problems, but after I saw Roman's list, which is much bigger than mine, I am definitely convinced that this is just a little subset of the problems that the syntactic conception of theories has presented through the years. There is one problem that he didn't mention much, and that's the problem of inconsistency. I take it the positivists were very keen on theories being consistent set of sentences, and therefore it boils down, that sort of results in the requirement that scientific theories must necessarily be consistent. And as we now know, there are many scientific theories that have all kinds of weird inconsistencies in them, so that's another reason to, if you won't, reject the syntactic account. And I'm not going to defend the syntactic view. I don't think we need to go back to the syntactic view, even though I agree with Roman, there's lots of things here that have been, the view has been criticized for a number of things that maybe it isn't entirely criticizable for. But then there are other critical points that can appear. So let's turn now to the semantic view, which is the view that replaced the syntactic view for whatever reasons, whether it be good or bad reasons in the 70s and 80s. And this has a number of supposed advantages over the syntactic view, gets supposedly over some of the problems. We now know maybe it doesn't get over the problem of defining the empirical content of theories or empirical adequacy. I mean, we'll have to discuss that. I still think the semantic view has some advantages over the syntactic view of this. But there's a number of things that you can do with the semantic conception of theories that you couldn't do with the syntactic. The syntactic conception, you can play around with languages, that doesn't affect the integrity of the theory. It's not linguistically relativistic in any way. You can also have inconsistent theories, and in principle that's not necessarily a problem. So there are a number of putative advantages, and that's why I'd like to come up with a version of this view that is defensible. Okay, so what is the semantic conception? I think typically the semantic conception is characterized by means of a very vague statement of the essential identity of a theory. I find many people summarize the semantic view as the claim that I've written here on the top of this slide. A theory is just a set of models. It's not a set of sentences. In any language, a theory is just a set of non-linguistic entities, namely models. But that often comes together with, and often in the very same description, a view about what models are. So often people would say the semantic conception is the view that a theory is a set of models and a model is blah. And so I want to distinguish these two claims very cleanly, because I think that while the second claim that has often been advanced on behalf of the semantic view is controversial, the first claim need not be so, and particularly when you distinguish them. But it's quite clear that if you combine these two claims, then you get a more a complex expression of the semantic view that says something like a theory is a set of X, whatever models are. If models are X, then a theory is a set of X. So here's one way in which this gets very often filled in, to the point that sometimes it's almost presented as if this was the view. This is the semantic conception. Call the first claim the semantic bird claim. I'm going to call it the semantic bird claim because I think that's the only really essential claim on behalf of the semantic conception of theories. Theory is a set of models. And I'm not even sure that full identity is necessary. You could also have a characterization of this view that says a theory can be helpfully construed for whatever purposes as a set of models. That's enough, I think, to fill in quite a substantial claim about the structure of scientific theories. And I'll come back to this at the end of the talk. The second claim that this is often accompanied with is the claim that models are structures, called out the structural claim. Now it's quite clear if you put these two together, then you get what's normally known as the semantic conception of theories, and that helpfully Roman was talking about earlier today. He already mentioned that he was really talking about this version of the semantic conception. The idea then is that the theory is just a set of theoretical structures, or structures more generally. I'm not even going to refer to set theory. Let's just talk about mathematical structures more generally, where a structure is just a domain of given domain of a set of objects endowed with a number of properties or relations. And we just write it that way. That's the structure. Separate the domain and the relations, and therefore on this version of the semantic conception of theories, a scientific theory is just a set of those things, a set of structures. Now this is the view that has been subjected to much criticism over the years, not least by me and many others. And here's just again a list that's probably quite a subset of all the problems that this view has been found to have, and that I think if you have ever a convincing philosophical argument against a view, this combination of different objections strikes me as convincing as one can be, as any combination of objections can be against a particular view. So this is some of the points that have been raised, some of them by myself. The view is biased towards the mathematical sciences because it puts the concept of mathematical structure at the core of scientific theory, but not all scientific theories are mathematical theories, so therefore it seems that it leaves out a lot of what goes on in scientific theorizing. Many theories, in fact, are not on the face of it structures, and sometimes that's also the case even in the mathematical sciences. So that's pressing concern that even in the mathematical sciences you cannot easily identify a theory with a set of structures. It's been said about the view that it's unable to account for methodological practice in the sense that scientists go about building theories and testing them in ways that do not seem to involve, on the basis of it, any structures or structural relations. It has been said, and this is a point that I will return to, it's a point that I want to stress, that it is unable to accommodate the practices of idealization and abstraction in particular, and the fact that many models are idealized or abstract, a point that I will return to. It's unclear what the cognitive and epistemic foundations of this view is. I mean, most scientists are not mathematicians and therefore not necessarily particularly well trained in the use of mathematical structures. Nonetheless, this view is supposed to apply to all scientific theorizing regardless of the cognitive and epistemic credentials and knowledge of the scientists. And finally, the final objection that I hear often, and I think Roman kind of presented a version of that objection here, is that when it matters, it really is not that different from the syntactic view anyway. So a lot of the problems of the syntactic view carry over to this structural version of the semantic view. For all these reasons, you may be tempted to reject the semantic conception, and I have been very tempted throughout my life. I have rejected it many times, in fact. But it somehow keeps coming back, right? So, what I want to do in this talk is to see what can be salvaged from all this criticism of the semantic conception. And my idea is that if you just focused on the semantic bare claim, not on the structural claim, then in fact a lot can be salvaged. And it may even be quite interesting to have a new version of the semantic conception along these lines. So here's the alternative that I want to look into. I won't say that I want to defend, but at least I want to look into, and I'd like us to reconsider. The view that gets rejected is a combination of the semantic bare claim and the structural claim, but I want to ask how essential is this structural claim for a semantic conception of theories? If the semantic basic claim, the basic claim of the semantic conception of theories is claim number one, then it actually wouldn't seem to be that essential. There is no reason why the structural claim 2 needs to be true in order for the semantic bare claim 1 to be true. At least it doesn't appear on the face of it to be any necessary or logical connection. So my suggestion is that we substitute the structural claim by a different claim, which I'm going to call the representational claim, claim number 3. Namely that models are not structures, models are representations. What I want to look into is the viability of the view that conjoins the semantic bare claim number 1 with not the structural claim number 2, but the representational claim number 3. And what you get there is some kind of representational version of the semantic conception that simply says that a theory is a set of what? Representations. Okay? So, on the face of it, as I said, this looks quite different, but of course it wouldn't turn out to be very different if, in addition to this representational claim 3, you were to defend something like this structural additional claim 2 prime that says that every representation is a structure. Because then you go back to where you started. I mean, then you just have a representational semantic conception that tells you that theory is a set of representations, but if you add the structural claim 2 prime, that representations are all structured, you go back to the structural semantic conception, which I've noted is unviable. Theory is a set of structures, that one thing that we don't want to end up with. And you would end up with that if you accept it. So it turns out to be critical, I think, for the prospects of the semantic view, not to accept the structural claim 2 prime. That claim, I think, must be false if the semantic conception is to live. As a matter of fact, I think there's lots of reasons to think that the structural claim 2 prime is false. So, if you follow me, if that claim is false, then there is a version of the semantic conception, the representational semantic conception, that does not boil down to anything that we could possibly object to, on the same grounds that we object to when we object to the structural version of the semantic conception. Okay, so this is therefore the thesis. that I want to defend in the talk, namely that this claim is false. It's not true that representations are structures, and moreover, I think that's not true, and we have good empirical and conceptual arguments and reasons to know that it is not true, that this view is false. So I want to defend that representations are not in any way structures, they're not constituted by structures, and that's true even in the mathematical sciences. Even in those cases where structures are used as part of scientific representational work, it is not even the case in those sciences that representation in those sciences boils down to structures. So what I'm going to need, therefore, is an account of representation. And you all know me, so you know that I'm going to defend an account of representation on which representation will not boil down to anything like a structural relation. So just to run you quickly through the different accounts that have been canvassed of representation in the field in recent years, and many of us we've been working on this for some time. I like to distinguish them into two kinds: the substantive and the deflationary accounts. And the substantive accounts are the accounts that try to understand representation or define it in terms of either some kind of a structural morphism or some notion of similarity. And the deflationary accounts are accounts that do not try to define representation in terms of anything, and certainly not in terms of the structures. And the two that I most have discussed in my work are the denotation, demonstration, interpretation account of Rick Hughes, and my own inferential conception of representation. Now, this text over here indicate those accounts on which, at least at first sight, there's no suspicion that they will boil down to anything like the structural claim 2 prime, which is the one that does all the bad work for us in getting us to the wrong version of the semantic conception of theory. So, in fact, there's lots of different options, I think, here. We can play around with lots of different views of representation that will avoid the problems, as long as we don't fall for the isomorphism here. Okay, so now what I want to do in the rest of the talk is, by using something like a deflationary account of representation, I want to, something very close to my own account of representation, I want to argue that the structural claim 2 prime is false, both conceptually and empirically. And in order to do that, I want to distinguish two kinds of questions. And so take all of this as a defense of the representational semantic conception as part of an inferential account of representation. But I'm already telling you there are other ways possibly of doing this that are not objectionable, because they don't boil down to this structural claim 2 prime that I think is the one that creates trouble for us. So as long as you don't go for isomorphism, I think in principle you're going to be fine. But I'm just going to care about my own version of this. So I want to distinguish two different questions, and this is the bit of the work that I've did most jointly with Francesca. We've distinguished two kinds of questions: a question of constitution and question of application, or more generally, questions, since there are many questions of application. There's only one question of constitution, but there are many questions of application as regards scientific representation. So the question of constitution could be put in this way. You ask yourself the question: for any representation of any target system by any model, any B by any A, or B and A can be in principle anything. B is whatever gets represented, A is the scientific model. That's a representation. And for any representation of B by A in any context and at any time, what is the relation R between A and B that constitutes representation? So this is a pretty grand question. It's one universal question, if you want. Questions of application, however, are as many as there are instances of representation. For a particular representation of a particular system by a particular model, in its context of use, at the time of its use, what is the relationship between A and B that agents use in that context for surrogate inference to conclusions about B from A? Anyway, those of you who know my inferential conception, that surrogate inference is the only thing that is at the core of scientific representation on my view, so this question is pertinent to representation on my view. But this is a particular question that you ask and may answer very differently in every instance of representation, right? Okay, so a deflationary account will take it that the question of constitution has no answer. So a deflationist will defend that there is no relation R that in general constitutes representation for any AB in any context, in any time. But moreover, no such answer is needed in order to provide informative answers to the question of application, to the different questions of application. No answer to this question is going to be needed in order to do a lot of detailed work about how different representations work in their particular context at the time of the use, as used by the agents that employ them as surrogate inference vehicles. So, for a given representation of any B by any A, in its context of use C at the time T of its use, you may have a particular relation between A and B, the relationship RCT, indexed to the context and the time of the use, that agents employ for surrogate inference to conclusions about the target from the source. And this is what I will call the means of application of the representation, which, as you can see, is extremely contextual and is also very much time-dependent or time-relative. So the same model and the same system may have different means of application in different contexts at different times. And the relationships that between model and system, between source and target that get employed in surrogate inference may well change from one context to another. That means the means of application are always possibly changing. Now, if you accept this, then I think there are good arguments have argued in different places. There are good reasons to think that something like a deflationary account of representation is needed, or perhaps in the terms of Agnes this morning, it occurred to me the way to put it is that a deflationist would say that representation is not a concept that admits of Carnapian explication. While a substantivist is someone who thinks that there is some kind of explication that is needed for the concept of representation, and then people argue as to what that explication may be. And Carnap accepted that there were some concepts for which the project of explication was not viable or applicable. Not every concept was susceptible of scientific explication. So a deflationist thinks that that is true for scientific representation. It's not the kind of concept that you can have a theory of or an explication. Certainly, if you understand explication as providing necessary and sufficient conditions, then that's certainly going to follow from the deflationary account. Okay, so if you buy anything like this, then it follows almost automatically that the structural claim 2' is false, conceptually. Because if there is no structural answer to the constitution problem, then there is no structural substantive account of representation, and you cannot generally say that a representation is a structure. So this claim is therefore conceptually false on a deflationary account of representation. Now, what I want to do in the rest of the talk is to try to argue that the claim is also empirically false. In addition to having conceptual reasons that derive from whatever reasons we have for a deflationary account of representation, we also have empirical reasons that indicate that nothing like a structural claim 2' is in any way along the right direction, and we should abandon it also on empirical grounds. So in order to show that on empirical grounds, I have to make reference to case studies. And of course, there's a bunch of different case studies one can use in order to illustrate this thesis and show that a structural claim 2' is false empirically. But I'm going to pick up two that are particularly powerful in the sense that are extracted from instances in which I think mathematical structures do play a role of some sort as means of representation. And they're extracted from two cases of very evident mathematical scientific work in two different disciplines. We could discuss a bunch of other examples, but they seem particularly pertinent for that reason. So the argument is, even in those instances of scientific modeling work where you expect something like the structural claim 2' may be true, even in those cases it is empirically false. So the two cases I want to look at are well known. One of them has appeared over and over already in this conference. It has become incredibly popular, this model, the Lotka-Volterra model in population ecology. Everybody uses it all the time now. And the other one I want to refer to is Brownian motion and statistical mechanics. But you could also have looked at single harmonic oscillators. You could have looked at classical mechanical descriptions of particles under motion in phase space. You could have looked at a bunch of different models from highly mathematical parts of science, biology, or physics, where something like the structural claim could be right, and nonetheless it fails. So let's look at this one first. So the Lotka-Volterra model is a model of prey-predator relationships. It's a nonlinear couple of equations. X is the number of prey, Y is the number of predators. So it's measuring some quantities, and often invoked as an instance of mathematical scientific representation by means of a structure. And well, the first thing that may pop at you when you see this is, what is the structure here? But you could begin to talk about the structure of these equations, but that doesn't look like the right place to look for a structural match between the model and the target. Of course, these equations have some markers, and therefore you could perhaps talk about that. But clearly, that's not what we're talking about when we're talking about the structural means of representation. We're talking about the kind of structures described by these equations abstractly being in some way morphic, holding some kind of morphic relationship to some ecosystem. So what we're really looking at is the kinds of graphs that have already appeared in this conference, in which you look at the variability, the dynamical changes in the values of the two variables. And then the idea is that when you compare these changes in the quantities of these variables to a real ecosystem in the Adriatic Sea, you will see that they correspond. So the same variations in prey and predator that occur in the model roughly occur also in the ecosystem. So how is this structurally morphic? Well, the relationships between these two quantities seem to be preserved. As they change in the model, seem to be preserved in the ecosystem. Now, as you know, this is actually, I think we all know, this is actually incredibly complicated, because Lotka and Volterra never really described any specific ecosystem. This was a description of extremely abstract idealization of what was going on in the Adriatic Sea. So if anything, this model is morphic, or is related in some kind of morphic way to some very abstract ecosystem of fish and different fish in the Adriatic Sea that is in itself already an idealization. Now, this is a point that I will come back to. So if these models, which are highly mathematical and supposedly the prime candidates for structural representation, if they do actually represent by means of morphism, what they represent is extremely abstract and idealized, and not really any concrete system. The same thing goes for Brownian motion. You can define it by means of a number of conditions on a stochastic process, impose a number of statistical conditions and dynamical conditions on this stochastic process. Of course, the kind of structural relations that we're interested in are not so much the relations that occur between these mathematical symbols, but the relations that occur between the kind of abstract, the structures that are described by these processes, something like this motion of this little dot in this phase space. And this is supposed to be structurally morphic to the motion of some dot of dust in the air in some place or other at some time. Well, I don't think so. I mean, this is if it is morphic to anything, it will be morphic to a very abstract and idealized dot of dust in a very abstract and idealized building, room, and so on, subject to very, very idealized conditions. So you can see already how this gets complicated, because even in the best possible cases, the best thing that we can say is that in different cases, different morphisms will obtain between the mathematical structures described by the equations and some kind of very abstract, idealized version of the phenomenon. Okay, so These different structural relations that do obtain, different morphisms that do obtain in this case of highly successful mathematical representation, are means, I would say, of mathematical representation, of scientific representations in this context, at these times in which they may be used for this, relative to these very abstract idealized systems. But I claim they cannot be constitutive of representation across all contexts. This is the first point I want to make. You cannot go from this to a claim that structural claim 2' is generally true, that all representations are structured. Why? For a number of different reasons. First of all, they display the wrong logical properties. All these morphisms are minimally reflexive. They're at least minimally automorphisms. And we know representation is not reflexive in that way. So the prey-predator model clearly is morphic to itself. And therefore, on this account of representations constituted by structures will have to be reflexive. That's clearly not the case. They're not universal, not even in the mathematical sciences, because you don't get the same kind of morphism across all contexts, even within the mathematical sciences. There are different kinds of morphisms. Different morphisms will obtain in different contexts. And finally, the point that is most important, they cannot accommodate the varieties of idealization and abstraction. And this is the point that makes the case that even empirically, the claim that all representations are structures is false. And this is very much linked to the ubiquity of the phenomenon of misrepresentation. Now, Agnes was talking about this morning, and she wasn't convinced about it. I'm one of those people who has been constantly beating the drum of the misrepresentation. Maybe there is not a very good name, misrepresentation, because it does sort of suggest a failure of representation. So then you're tempted to think that maybe there's no representation going on. But I'm keen to distinguish misrepresentation from no representation. So misrepresentation is rather something like inaccurate or inappropriate or maybe not particularly helpful representation. There's a case of representation. If you think about it in that way, then all models are misrepresentations in the sense that they're all inaccurate to some extent, in some respect, to some degree. They're either idealized or abstract or inaccurate. So if all models are misrepresentations in this sense, then any account of representation has to account for this. Well, you know that I don't think you can have a structural account of representation that does justice to this third point. So very quickly, the reasons to suppose that nothing like this is forthcoming as a constitutive account of representation. They display their own logical properties because all those structural relations that can play a role in this context are at least minimally automorphisms. They minimally satisfy that condition. You can, in other words, you can always map them onto yourself. The minimal thing that you can do with the structure is to map it onto yourself, and then you get a structural mapping or a morphism that automatically guarantees that the representation is reflexive. But we know representations typically or generally are not reflexive. The second problem which I mentioned, which was that they're not universal, not even in the mathematical sciences, is borne out by the fact that often the state space is merely a mathematical tool for prediction. This is, for instance, the case in quantum mechanics, where if you have a vector in Hilbert space, you shouldn't take that to represent in any way the position of a particle in physical space. What you do is you square the amplitude, and that gives you the probability of finding a particle in a particular place. So there's nothing like a morphism between the state space of quantum mechanics and the physical space position or any other quantity, dynamical quantity of a quantum particle. So very often, even in the most mathematical sciences, you get nothing like a universal morphism operating as at the point of the application of the representation. And finally, the point that I want to make here, which is the one that's, I think, most obviously making the empirical claim against the structuralist claim about representation, is that idealization and abstraction in structural terms turn out to pull in different directions, which you cannot in any way reconcile. And this is part of work that I've done with Francesca. So if you think of representational sources and targets as structures, and then try to characterize what goes on when we have an abstract model or an idealized model. You can have different representations of what this is like in structural terms. And we say, for instance, that abstraction can be treated as the following phenomenon. We say that a source abstracts some property in a target if and only if there exists some set of objects in the domain of the target structure, such that there is a property or relation obtaining in the target that is lacking in the source. So the source is abstracting away from the target. There's some rich properties of the target that the source is ignoring. The source is a streamlined or abstract version of the target, and that's what the phenomenon of abstracting away boils down in structural terms. You have something like that obtaining in the case of an abstract model representing a target system. In the case of what we call pretense, which is a version of idealization, you have the opposite phenomenon. A source model will pretend some property in the target if and only if there is some n-tuple in the source, some set of objects in the source, such that there is a property or relation obtaining in the source that's lacking in the target. And here, the mappings take this form because when you define morphisms between target and source, you normally have the mapping defined from the target to the source. So you can have a well-defined notion of homomorphism and so on. So that's why you get the inverse function here. It's slightly counterintuitive, but that's how it works in the mathematical definitions of these types of morphism. So what happens here is that the source is introducing properties. There's properties in the model that are not really in the target system. You're introducing them in the source because you're idealizing the target away, introducing simpler properties or simplistic descriptions that will, for whatever reasons, become more tractable in the model. It makes it easy to work with the model once you introduce these properties. So this is a kind of idealization. And most models do both. They do both abstract some of the properties of the target and also introduce or pretend that there are properties that are not there. Think about, for instance, the billiard ball model in the kinetic theory of gases. That model sort of abstracts properties away from the gas molecules. There are a number of properties the gas molecules have that are not represented in the billiard ball model. But it also introduces properties of its own that are not really in the billiard balls, such as color, shininess, hardness, and so on. So you have, and all models play around with both. They introduce both abstract and idealized properties. Now, the problem here for the structural claim about representation is that there is no kind of morphism that will accommodate both abstraction and idealization. Those kinds of morphisms that accommodate idealization do not accommodate abstraction, and vice versa. So this is what we've shown in a paper. This paper is actually already published. It came out in the European Journal for Philosophy of Science a couple of years ago. And what we showed there is that when you look at the mathematical definitions of the different kinds of morphisms, homomorphism, epimorphism, or full isomorphism, you cannot, by means of any of them, accommodate all of the phenomena of idealization and abstraction that goes on in modeling. So, for instance, homomorphism accommodates pretense. You can accommodate pretense with homomorphism. You can accommodate the idea that the source model is richer and incorporates properties that are not really in the target. Okay? Not every property has to get mapped onto when the morphism is a homomorphism, but you cannot accommodate abstraction. Epimorphism is another kind of morphism that is not often discussed. There's a variety of this, which is often implicitly invoked in these discussions. That accommodates abstraction but not pretense. And full isomorphism, of which partial isomorphism is just really a subcase, very little difference between full and partial isomorphism, accommodates neither abstraction nor idealization. So empirically, it's impossible to have one morphism giving an account of all instances of representational means, even in the most mathematical sciences. So, I hope to have shown that the following claims are empirically and conceptually false. I don't think it's true that a model is a structure, and I think we should really fight this hard. Don't believe it if you see it written anywhere. But I also don't think that a representation is a structure, and this is something that I've been saying for a very Two prime is something I've been saying for a very long time, that I don't think that's true. And if that's the case, then it becomes untenable on any version, however you try to do it, that a theory is a set of structures. So it can be identified with just a set of structures. So I think the structural semantic conception is false. And Roman was, in his talk, was really talking about a version of this structural version of the semantic conception. And I think indeed those structural versions don't work. But this does not mean that no version of the semantic conception will work, because what I have said really has no bearing on any of these two other claims when you understand them properly and independently of the other two. It may still be the case that a theory is a set of models, or can be helpfully construed for some purposes a set of models. And I think it is actually true that a model is a representation. So it may still be true that the conjunction of these two claims is viable as a view on the nature of scientific theory. Namely, that a theory is, or at least for some purposes, can be construed helpfully as a set of representations. And if you have followed me all the way, you will have seen that there are reasons to think that this is a version of the semantic conception of theories, because it respects the very bare claim of a semantic view, namely that a theory is or can be helpfully construed as a set of models. And I think when you reread some of the things that Van Frassen and Suppies wrote in a sympathetic spirit, you can see them hankering after this. And certainly someone like Ron Geary has always leaned towards something like this, much more than anything structural, without ever making it very explicit. So I think it could be worked out, and it's still viable. Something like this semantic conception of theories may still work. Okay, that's it. And that's my final conclusion.
Yes. I have a clarificatory question about representational claim number 3. I didn't hear a reason why. Maybe you think you don't have to give one. Why a model is a representation? Because when you gave us reasons why representations are not structures, you gave a lot of reasons why they are not. You talked about seeing representations not as substantive as deflationary, and for that not the DDI model but inferential. So is the model inferential or deflationary representations as well? They have a different sense of representation here.
So, I think this claim may go, certainly it goes through on my view of what representation is, because my view on...
What is it?
I've been talking about this for so long now, for so many years, that I'm sort of so bored of it that I no longer want, but it's basically the view that representation is just minimally surrogate inference. Not even in action, but in potential surrogate inference. So the capacity that a model has for an agent to provide inference about a target, and the inferences need not be to true conclusions about the target. So it's an incredibly minimal condition on representation, so a lot of things turn out to be representations.
Models provide inferences.
Yeah, exactly. So the reason why I believe the claim 3 is true is that since my account of representation is so thin, I don't know of any model that doesn't satisfy it. But I'd like to add to that I don't think you have to you don't have to marry my account of representation in order to make this claim work. There may be other accounts of representation. Certainly I think it goes through on Hughes' account, the DDI account, which is another deflationary account. But it may well go through on the similarity account of representation too, particularly if you have a very, very trivial notion of similarity, or almost anything is similar to anything else, then by default, a model will be a representation if representation is just the holding of trivial similarities. So there are different accounts of representation where this is true. And in fact, I don't think of that as a particularly controversial claim. I think the Baird claim is the one that people have contested. But as I said in this talk, I think often they've contested it because they conjoin it with another claim out of which they get something that is clearly problematic. But if you just take it on its own as a bird claim, then I think maybe it's not so bad.
Thanks for the really great talk. One thing that I'm sorry, that strikes me, which is slightly different than one of the usages of the ambiguous word model in your representation semantic conception, is that many people talk about models as having somewhat different scope than theories. Like Morrison talks about models as mediators between very abstract theories and concrete models. And you would find theories or frameworks as means of producing detailed models, constraining producing, something like that. How could you account for this, and could you be able to do this?
That's a really good question. It's a very good question, because I was part of that Models as Mediators project, and I have a paper in that book. So we were defending this view that indeed the semantic conception is false, because the bird claim is false, because theories are distinct from models, because they're actually employed in producing models, and models mediate between theories and data. I'm not claiming this is necessarily consistent with that. I mean, this is a different view. This is a different view. It's an attempt to make good on the semantic conception. It's the best attempt that I can make on behalf of the semantic conception. And I don't think it's as objectionable when you look at it in this way as I thought, say, 20 years ago when I was working on the Models as Mediators project. Then I really thought the semantic view is a no-go area, you shouldn't go there at all. Now, when you look at it this way, once you detach it completely from the structural leanings, from the structuralism, then I don't really see that much that is objectionable in it. It certainly erases the boundary between theory and models, evidently. So when you want to tell a story about how a theory is used in constructing a model, you may, in this kind of framework, collapse the distinctions, but you can still say, well, here's a complex set of models that have been used in some kind of instrumental way in order to build up some other model over here. I mean, I think you can still make that claim, but it's not going to be a generic claim about how theories are distinct from models, because on this semantic conception they are not. I mean, theories are just bunches of models.
I thought you would answer that theories in that older area. Let me just see whether you would say that I'm right or not. That theories would be in some ways abstracting away from the detail you get in models. So they would be like abstractions from what you get, because that seems to be...
Yeah, I mean, that's part of what goes on in the volume. In Models as Mediators, some of the people who were involved in that project, I wasn't one of them, but there were people who thought of theories as abstractions, and the models are kind of concretizations of the theories. I guess you can still, in this framework, you can still tell that story, but it's not going to be a story about theories getting concretized in models. It's going to be a story about theories getting concretized in smaller theories, or sets of models getting concretized in more concrete sets of models. You can no longer cleanly distinguish the theories from the models. But again, my claim is that perhaps we threw away the baby with the bathwater. We threw away the semantic bear claim which didn't need to be thrown away, with the structuralist water, right? Threw away the structuralist water, and the semantic baby went along with it. But perhaps the semantic baby could have been preserved in its bare babiness.
Sorry.
So I have two related questions. One is just about how you see this project, in particular whether you see it as sort of a minimalist defense of the semantic view of theories, analogously to the way that you've been talking about representations, because it seems like what you've done here is stripped it down to its bare
Yeah.
bones and
Yes.
seen
Right.
and kind of tried to determine, okay, what can we save it in
Yeah.
some, like the essence of the semantic view?
Yeah.
What is the essence? Semantic bare claim number one.
Yes.
We can support it with this representational claim, and we can still
Yeah.
support it. So that's my first question. And then my second related question is, what is the goal, like the greater goal of the project, in the sense that if it's so minimalistic that a theory is a set of representations and you don't say anything more than that, then couldn't a theory just be any old set of representations? In other words, couldn't we construe a theory in a way that we wouldn't intuitively think it qualifies as a theory? So just take the London Underground map and the Lotka-Volterra model and the pens on paper system and put them together, and then there's your theory. Is there, should there be further constraints to exclude just putting together any old representations that we might not consider to be models, genuine models? I mean, the ones I chose just now were, I guess, possibly models, but couldn't you just take any representations that we wouldn't consider to be scientific representations or scientific models? And
Yeah, I mean, that's a good question, because although I think all models are representations, I don't think all representations are necessarily models, and certainly not all of them are scientific models. So that's a good question, and I think yes, there's some leeway to go down that path and explore the different kinds of representations and how they can come together under a particular umbrella, a theory. I guess what I would say is this very minimal conception of theory doesn't tell you anything. I mean, there may be other constraints you impose on theories, but they won't be identity constraints. There will be constraints about what are good theories for you and what aren't. I mean, so there's lots of different motley collections of models put together that are no good for any purpose. I mean, on this view, they're a theory in some way, but they're not going to be a particularly useful theory for any purpose. So, but the reason you discard them is not that they're not a theory; it's that they're not the kind of theory you want. But of course, there's going to be lots of different reasons why you would want to discard certain collections and not others, and that's down to the pragmatics, which is the scientist's business. And as for the general project, I mean, that's a good question, which of course I've been asking myself a lot with Francesca. Francesca wanted to rescue the semantic conception, and initially I was like, why would you want to rescue that? But I mean, I'm sort of convinced that it is rescuable now. And moreover, I think I'm beginning to think it is kind of promising in ways I didn't suspect before. For instance, here's one way of thinking about it I think is promising. I don't know if you've read or looked at Rasmus Winter's entry in the Stanford Encyclopedia of Philosophy on the structure of scientific theories. So Rasmus does something interesting there. He says there was the syntactic conception, then there was the semantic conception. They're all wrong, of course, because we're Stanford people, and we think you need the pragmatic conception of scientific theories. And so the pragmatic conception is all that you can expect and much worse. I mean, all these pragmatic things go into the structure of theories and so on. But then he does something really astonishing, which is that he builds all these pragmatic features into the notion of a structure, and then links up the theory to a structure. And then he says the pragmatic conception is this unified structures that have all kinds of different purposes. You have to take into account the agents, uses, and so on. But when you put these pragmatic structures together, you have a theory. Well, I think that's just the wrong way to go. And now thinking about this, I think this is a much better way to go. You forget about the structures. Forget about bringing any pragmatism into the notion of a structure. It is not the kind of notion that you will want to go pragmatic on. It's a very well-defined mathematical notion. Leave them alone and just bring the pragmatism into the representation, as for instance you do with the inferential conception or the DDI or any sensible account of representation. Will take it that those pragmatic elements are really essential to the representation. They're not incidental. They're not just questions of application of the representations in context. They're really part and parcel of what a representation is. Once you have the pragmatics into the representation, then you can just run the bare claim. Theory is totally construed as a set of representations, and all the pragmatics is already in there. So you have a pragmatic conception of theories. It's already sort of in there. So this is an easy, cheap way of getting what Rasmus wants without getting all these complications with how structures can be pragmatic, which, to be honest, I don't follow him. I can't understand what it means for a structure to have a particular use. Or, I mean, structure is just the structure. So I think that's the general project is now, thanks to Francesca, I think, you can use some very minimal version of the semantic conception to get all the pragmatism that you want into the nature of theories. That would be the big project that is now left to do. This would be the starting point. Yeah.
Okay, Robert.
Yeah. Well, my first question is very similar to Agnes' question. So, the main action in your argument is showing that models are in structures.
Yeah.
But I'm not sure what you want to say about what makes a bunch of models a theory. So, in response to Agnes, you just said it's pragmatic constraints, but that can't be everything. If you want to understand what is Hamiltonian mechanics, the question is not what do we find useful to throw into the basket. So it must be more. There must be relations between these models. There must be some sort of structures there. So a theory can't just be a bag of representations, whatever these representations are. And I wonder how you conceptualize this sort of in your approach. I mean, to be fair, in most of the semantic view versions have said preciously little about this too. So I mean, this is not only a problem for your approach; it's a general issue for that family of approaches. And I just wonder whether you have any thoughts about how you want to deal with this.
Yeah, good question. Yes. I don't have many thoughts now. I'm just starting to think about. I mean, this general project is just something I'm starting to think about.
Because that's sort of from what's in the back of the question is, I mean, I don't like the structuralist version, but one thing that structuralism does well is deal with formal similarities. I mean, if you think your theory is a set of structures, you can say that a theory is defined on a bi-invariance group, or if you want to go on a category theory, you can say it's a category where the arrows have certain structures. I mean, you can go as fancy as you like. You can tell a story there. You're sort of losing that if you lose structure of it. And I just wonder what you want to put in its place.
Yeah, I guess one could go down the wrong geary. The way Ron would answer, I think, your question is by saying, okay, so classical mechanics, yes, it's not just a bunch of models. There are a number of principles there as well that we sort of employ in building the models. It's not just a bunch of arbitrary models put together, of course. It's not, because otherwise you could just put any two models from quantum mechanics and claim that's a theory. So obviously that's not the case. So there must be some...
All the models that have been mentioned in this workshop.
Yes, all of them together, and that's the workshop's theory.
It's very useful for those who have to write a summary of the discussion.
Yes, but for no one else. So there must be some generating principles. Yeah, that's a good question. It goes back to your question. It goes back to your question.
Yeah.
So there must be some kind of generating principles that are sort of the ones that implicitly delineate the set of models. I mean, the one thing I know I don't want to do is to run the Friedman version of this objection on Van Frassen. I don't know if you know this in the review of the scientific image, Friedman has this argument against Van Prassen, and says, well, if scientific theory is just a set of elementary models, then that's just a syntactic view. But it turns out elementary has a very precise meaning in model theory. Namely, all the models that make true a bunch of axioms of first order logic. So you basically get your syntactic conception through the back door. And Van Prassen's answer to that was, no, there don't need to be an elementary class, so therefore the set of models do not need to all satisfy a particular set of axioms, so it is not equivalent to the syntactic view. So obviously I'm not going to want to fall into that, but like Van Prassen did in the response, but it's true that that just remains too loose. So there must be something else. And maybe since we've gone to the pragmatics, one way to look at this would be to look at the principles that were used in generating the models that make up a particular theory. So in classical, which is basically the Geary story. So in classical mechanics, the three axioms are not just syntactic axioms for an elementary class of models. They're actually rules of thumb that you employ in the construction of any classical mechanical model. You sort of use them in order to build up the models. And so something like that must be put in there. Yeah, thank you. I mean, there's something like that must be added into this account. Yeah.
Sure.
There is actually you could look at from another point of view, not from generating, but actually on testing or confirmation. So John Watkins, for example, talks about organic fertility of theories. So a theory is organically fertile when you cannot chop it into different pieces, and you wouldn't find a single piece of evidence that would disconfirm all of them. Okay, right. So you have isolated islands in a theory, right. And then a theory is fertile if you could have an experiment or a piece of evidence that would overthrow all of them, because that's a single theory. And I think it's an interesting constraint on the structure of theories, which have to be very, very, not just logically consistent, because a conjunction does not satisfy it's something deeper. And I think there are lots of similar constraints which are very difficult to disentangle, but I would also think not only on generation, but
heuristic fertility, I think, strikes me as maybe even more promising than empirical adequacy of fertility. Yes, that's probably also a good suggestion. Yeah, thank you.
This is a very minor point in your account, but I think it might be worth worrying about. When you were talking about misrepresentation, you then went on and said, well, after all models misrepresent because they're all inaccurate. Now, I think they're all inaccurate in the sense that, you've abstracted or you've simplified or you've augmented or you've done something, but I don't think that makes them all misrepresentations. Because I think what I would want to say a misrepresentation is something that either misleads or is likely to mislead. Yeah. And so the mere fact that it's not, it's not isomorphic or something wouldn't make it misleading. So I think that something or other about misleadingness or potential, or not just potential in some, surely somebody can get confused sense, but there was something about the model that invites a misreading. That's what I would want to say is needed for misrepresentation. And I think you can get that.
That sounds right. That makes me feel a bit guilty because I think I may have been partly responsible for introducing the term misrepresentation in this discussion as covering all instances of inaccuracy, idealization, abstraction, whichever way in which a model is not fully and completely faithful. I at some point early on, I put this name on this, and it may have caught on. And I think you're right, it's not a very appropriate name. And Agnes was basically talking about it this morning, and I think you can get confused about this. in different ways. So if misrepresentation is about intentionally maybe misleading,
Or even, I don't want to make it all intentional because I don't
Yeah.
think there's any plot there. But I think that, if you set up a representation in some way that it's no surprise that people who are in the know get misled by it.
yeah.
So you're,
Sure.
So it
But
can be a
then-
mistake.
Then that seems fine to reserve that term for that particular instance of idealization, obstruction, or inaccuracy. But what would you suggest as the general term to cover all cases of?
Inaccuracy?
Well,
That seems to be what,
abstract models are not necessarily inaccurate.
okay, maybe inaccuracy and or incomplete.
Yeah, then there's two terms already: inaccurate or incomplete.
But it may
So-
be that we're talking about two phenomena here. One is where you simplified something so that it is no longer an accurate portrayal of the phenomenon, and the other is you've only told part of the story. And I think they're both characteristics, but we shouldn't necessarily expect a single term for both of them.
Well, when I started using the term misrepresentation, this way I was looking for a single term
I know.
that would cover all the cases in which models are not faithful and complete copies of what they represent, and maybe you cannot have that term, but misrepresentation seems in some ways the wrong term to use for that. Also because it suggests that Agnes's problem this morning, that a misrepresentation is somehow not really a representation. Well, the claim is these models are not perfect, but they're definitely representations. So I definitely believe that models are misrepresentations in this sense of the term. Maybe the term, yes, it'd be good to have different terminology. If anybody can think of a very general term for the very general phenomenon of the fact that models are not completely faithful to their target, all different kinds of ways in which they can be, that I think that would be helpful. A better name than misrepresentation.
So, if I may step in, I think that the term misrepresentation is at least currently being used just to refer to idealizations. So, in that sense, it's different from your original take.
Okay.
Good. Yeah. So
it didn't catch me.
It's not your fault.
Not my fault.
yeah, at least that's my impression, and I think this is how, for instance, Thomson Jones in 2005 used it, and Coteries made it in 2009. There are a bunch of other papers that deal with this. Usually it goes under the term distortions or misrepresentations. That is supposed to capture the term idealization.
So Martin and Peter were more careful. Right.
So, do you have a...
Well, if you have time,
Yeah, sure.
just for the sake of argument, let me play the structuralist here.
Oh!
So, the main argument when you had the diffusion model and you had the Lot-Commodera model is that look what these models are about is basically abstract thing. It's not a target system in the world, therefore isomorphism makes no sense. I think you could push back on that and say, of course, scientists speaking, it's not the way. But if you're serious about this, you ask a zoologist, and they name the predators in the Adriatic Sea, the baby sharks, whatnot. You name the prey, the red ones, the loose one. Just put them in. You define these two classes of fish, and you say that's what the model is about. It's a concrete thing. It has you can count the fish, so you can count the magnitude of these things. Sort of likewise with diffusion, we talk about classical mechanics, so you can label particles. So you can pick a molecule, you call it John, and you say that diagram that you have, just that represents the path of John.
It represents it inaccurately. most likely.
Maybe wrong. John may have taken it to turn somewhere.
Yeah, but who cares? Yeah,
so
it's
what's wrong with that?
Well, one of the things that's wrong is what I go on to say at the end, namely that those two models are abstract. In the case of the Lotka-Volterra, it's very obvious that they are. There's many more fish in the sea than these two kinds.
Yeah, but you could
But
say
complex interactions are just abstracting, and when you abstract, you're ruling out certain kinds of morphisms. So that's one problem. And then if you were to pretend on top of that, which the Lotka-Volterra doesn't because it's a very minimal structure, but if you were to introduce additional structure into the model, then you have pretend as well as abstraction, and then no morphism is going to get you out of that. It's in our paper. I mean, I was surprised too. So that I think won't work. So what do I want to say in that case? Well, I think you will have to run something like Nancy Cartwright's causal structures or capacities in order to make sense of these models as representing some real abstract features of these objects. So, I mean, I don't know what this concrete ecological system is, where there are only these two properties interacting in this clean-cut way. That's an abstraction of the real system, surely. And so the only way to make that a genuine representation of the thing is to say it's representing some abstract properties of that thing. And that may do, but I think it needs a lot of additional work. And, I mean, I love Nancy, she does wonderful stuff, but I'm not sure that the abstract concrete is something I follow. So
I could say something different. There, you don't have to go into unessential properties or anything like this. You just say there is one group of fish, there's another group of fish. The size of the group is a well-defined quantity. You just count them up and down, and the model just gives you the varying sizes of these two groups of fish. It doesn't pretend to be a complete representation of the area you see. Obviously, you leave out plenty, but once you've defined the group of predators and you've defined the group of prey, that is what the model defines. I agree that this is surely not how Lotka-Volterra talk about it, but sort of if you want to make a structuralist argument work, I mean, I think this is what they could say, and you don't need capacities or essential properties or anything like this. You just have to define two classes and their magnitudes. So.
Well, I mean, I have to think about that because I'm not. I mean, anyway, I have to think about that. I mean, one thing to say in response is that I've chosen what are the most friendly cases for the structuralist. So it gets much worse when you go to other models where, for instance, the mathematical structures are well defined or the equations aren't there. So these are supposed to be the cases that are most favorable to them. And even there I see problems. So for instance, this problem with what morphism obtains, what kind of morphism is it that obtains? There must be some structural relation. Even if it's true there is just the fish and those quantities that you're referring to by means of the model, there must be a structural relationship that is well defined. Well, I'm not sure there is. I mean, depending on whether you abstract or you pretend, you're going to have different kinds of morphism obtaining between. So there's not just one kind. So that already, I think, is a complication.
Yeah, okay, so I'm going to ask some questions.
Do we have time here? Like, I don't need to ask you.
4 minutes. So.
Okay, yeah, I mean, I'm just following up on this. Like, I was confused about why abstraction would be a problem, because aren't all models and indeed any representations incomplete in some sense? So I mean, don't we start from the assumption that we're never going to represent? Like, this is sort of something that everyone's kind of pointed out, that we're never going to represent every detail of every system. So why is this a response to Roman's objection that, well, we're not representing all these other things in the sea, this is very simplified? Well, I mean, of course it is, isn't it? Everything is simplified, it's just a matter of how simplified it is. So, yeah, I'm just like confused.
I mean, yeah, that is true, although that is already sort of, that already bites a little bit against the structuralist. I mean, there's the old Borges story, right? If you really demanded the isomorphism, if that's what you really demand, then there shouldn't even be abstraction. Models couldn't be abstract. So you really demanded full isomorphism. So clearly, that's not what you're demanding. You must demand full isomorphism.
But that would be, I mean, that would be like a full isomorphism between all of the objects in the. But I mean, couldn't we tell a structuralist story that's a partially isomorphic?
Yeah. Well, partial isomorphism doesn't actually get you out of many of these problems, but homomorphism gets out the abstraction problem.
Yeah.
In a homomorphism, you only pick up some of the properties in the target system, and they have to have a correlate in the model, but not all of them. So that's the way to get around the problem of abstraction.
Okay, I'm satisfied.
Yeah, but I mean, I said.
I mean, for now.
I mean, I find it remarkable that all these structuralist claims are abound around the place that are really unsubstantiated. For instance, about it's not isomorphism that can do the job to let you understand how models work. The best you can aim for is a homomorphism, and Supis is very clear on this, actually. Supis is very clear on this. But many other people haven't been. So you have to sort of be precise, and when you're really precise with the kind of morphism and how you define it, then you see that you're ruling some things out.
All right, so last question.
Very short. Let me pretend I'm a structuralist. So then, a lot of people in literature on models distinguishes between parts of models that have the representational function and those that are in some ways, helping the other things. And for example, Stevens would say that the idealization is in the part that does not represent. We're not confused. We know we have put the falsity there. We do not read falsity out of the idealized part. So basically, if you are a structuralist, you could go this way. You could say, of course there are parts of my model that have this property, but I don't think they have the relationship with reality. But the part that I think represents has this beautiful structural relationship that I'm talking about. So no longer idealization pretending is a problem, and with abstraction you could always say, I do not pretend that my model represents everything, it's always incomplete. So what is bad about this kind of move? How would you go against the Stevens?
Yeah, I mean, that's sort of an attempt to say, so that would be an attempt to recover a very robust, strong notion of representation that where there is no misrep, because the part of the model that represents the one that's actually fully accurate. Well, I just don't think that's the way modeling works. I mean, it's a model, in a typical model, the idealized bits are as functional and operative in getting the results out of the model as the non-functional bits. And I don't see many cases in which you can cleanly distinguish the non-functional idealized bits from the functional non-idealized and therefore representational bits. If there were clean ways of doing that, scientists would be doing that already, and you wouldn't have these complex monster models in which you mix both of the things up. So obviously that's not as trivial as the view puts it, and I think there are some good papers out there making the case that the kind of idealized bits of the model often are really, really important in getting the good results of the model out of the model. You couldn't get the predictions out without the idealized bits, and that's as regards prediction. But then if you move on to understanding, I mean, Kate has written a lot on this, then I think it gets even worse, because a lot of the understanding is not even connected to the predictive power, but it's connected to antecedent knowledge and so on. So it's even more relevant that the stuff in the model that is not fully representational is doing lots of different jobs for you, and I don't think you can just cleanly take them away. So yes, I don't think that this story really works in practice. There, that's one of those instances where you say this does not do justice to the scientific practice. So if it was that easy, the scientists would be doing it already. They would have gotten rid of the idealized, useless bit and have just stuck to the bit that does the actual representation. Clearly, that's not what they do. So.
Well, I don't think he would say Strivens that it doesn't do any work, but that we just don't think it represents reality, but it would be very helpful in making lots of inferences, lots of other work.
Well,
so
then
it's just a supporting role.
he's clearly using the word representation in a different sense than I use it, because if it's doing lots of good inferential work, then I'd say
Yeah.
that's what you want.
Yeah.
So clearly he has a much narrower
More.
view on what counts
With
as
truth
representation.
value.
Yeah, absolutely. Yes.
All right. So thanks again, Mauricio.